Good morning, guys. All right, so moving along through our chapter 8 in the textbook, guys, we're on our logarithms unit. Topic 3, 8.3 is called laws of logarithms. So very similar to stuff you did in junior high and grade 10 where we had exponent laws. Well, in this topic here, we have laws of logarithms. So we're going to learn how what those are going to be. So just general, guys, review the exponent laws over here. If you're multiplying two powers to the same base, then we can add the exponents x to the m plus n. If you're dividing two powers of the same base, you can subtract the powers like this. If we're taking a power to another exponent, we can multiply those two powers like this. If we have, this is kind of a radical in how fractional exponents work, but this is going to be the same thing as x to the m over n. Okay, so these are kind of the laws we did in grade 10 and in junior high, all of our exponent laws. So what we're going to do for example 2 here is we're going to evaluate a few logarithms and try to come up with the product law for logarithms. So the product law would be if you're multiplying two things inside the brackets like we're doing in this case, and see if we can figure a pattern with this guy over here. Well, log base 2 of 8 is equal to 3. Log base 2 of 16 equals 4. Okay, now 8 times 16 is the same thing as 128. So what I'm going to do is just, well, what's the same thing as log base 2 of 128? Okay, well, it's off the side here, guys. 2 to the 7th equals 128. Therefore, log base 2 of 128, so this answer should be 7. Okay, so the pattern we're looking for here is, well, log base 2 of 8, so this part is corresponding to this 3. The log base 2 of 16 is this part is 4. Well, how do we get the number 7 from 3 and 4 is, well, we add them. Okay, so the idea is log base 2 of 8 times 16 gave us the same answer as if we took log base 2 of 8 individually, so this part individually, plus log base 2 of 16, because this answer was 3, this answer was 4. 3 plus 4 gave us this answer of 7. Okay, so this is an example of the product law of logarithms. So generalized, so this is like for any base over here, and this guy's on your formula sheet over here too. We have log base b of m plus log base b of n. Okay, so this is a rule that we're going to have to use for the rest of this unit over here. So again, if you're multiplying two terms in the argument of the logarithm here, you can separate into two logarithms where you're going to be adding them like this. Okay, and this is what we call the product law of logarithms. Guys, we're just going to go through and we have 3 more similar examples of here. And in this example, we're trying to develop the quotient law for logarithms. So we're dividing two ones over here. Okay. So similarly, what we did the last one, we're going to evaluate these guys individually. Log base 3 of 243 is 5. So 3 to the power of 5 equals 243. Log base 3 of 27 equals 3. 3 to the power of 3 equals 27. Now, off to the side here, I'm just going to do 243 is this, 243 over 27 is the same thing as 9. So this is really the same thing as log base 3 of 9, and we know this answer is 2. So that means this answer over here should equal 2 as well. So again, what we're trying to get at is like, if we look at these guys individually, log base 3 of 243 and log base 3 of 27, we get answers of 5 and 3. Okay, well, when we're dividing them like this, we get an answer of 2. So how do you get the number 2 using 5 and 3? And the answer is you subtract them. 5 subtract 3 is equal to 2. So generalizing that to this quotient law of logarithms, log base b of m over n is log base b of m minus log base b of n. Okay, so looking back for the product law, when you were multiplying these two numbers inside the brackets, we can separate them using addition. For the quotient law, when you were dividing these two numbers inside the argument, you can separate them using subtraction. So these are the product and the quotient law so far. Okay, so For this guy here, we have log base 2 of 8 and log base 2 of 8 cubed. We know that log base 2 of 8 is 3. 2 cubed equals 8. Now, 8 cubed, let's go use my calculator here, is 512, okay? So I'm going to run a few lists over here. It's 2 to the 5th equals 32. 2 to the 6th equals 64. 2 to the 7th equals 128. 2 to the 8th equals 256. 2 to the power of 9 equals 512. Okay, so what is this? Is the same thing as log base 2 of 512, and we know that answer is 9. So that means this answer is 9. Okay, now the thing over here, we have an answer of 3 for log base 2 of 8, and we have this extra 3 here. So how do we get the answer of 9 using 2 3's? Well, it's 3 times 3 is 9. Okay, so the rule we're trying to get at over here is log base 2 of 8 cubed ended up being the same thing as 3 times log base 2 of 8. Okay, so this answer over here was 3. 3 times 3 gave us this answer of 9. So the power law of logarithms is log base b of m to the n, so the argument is being taken to an exponent inside the brackets, is the same thing as n log b of m. So it's almost like we can take this exponent and we can bring it down in front and use it as a coefficient over here as well. This is called the power law of logarithms, and we use this one a lot when we're solving more complex exponential and logarithmic equations over here. We're using this rule quite a bit. So guys, those are 3 rules that we have, and now for example 5, we're just going to start practicing these guys over here. So log base 6 of x over y. So this one here is an example where we're using our quotient law. So we're dividing x over y. This is the same thing as log base 6 of x minus log base 6 of y. Okay, so this is how this guy works here. Example B is a little bit more complicated. But if we have the square root, so how do we deal with square roots? Well, we can write them as an exponent of 1/2. Okay. Now the rule we had for our power law is that you have an exponent inside the brackets like we do here, is we can bring the exponent down in front. So this is the same thing as 1/2 log base 5 of xy. Okay, so the power law says we can take this exponent over here and bring it down in front as a coefficient. Okay, now what we're also going to do for this question is we can now use our product law. So our product law was, and guys, these are all on your formula sheet, so you do not need to have them memorized. You will, because you'll be using them so many, but if you're multiplying two numbers inside the argument, you can separate them using addition like we have here. So for this case, the 1/2 is still out in front, and I can put brackets. We can separate these two using addition. Now I'm just going to distribute the 1/2 to both of them. So the instructions for this question said, write each expression in terms of individual logarithms of x, y, and z. There's no z's in this case over here, but that's okay. Okay, so again, we're done. So this is an individual logarithm in terms of x, and this is an individual logarithm in terms of y over here. So we've kind of separated those like this. Okay, so we're going to come across some questions, guys, where we need to be able to use these laws to be able to kind of simplify a logarithmic expression. For C. Okay, so what we have here, we're going to start with, we're dividing 9 divided by cube root of x squared. So I'm going to make this one the log base 3 of 9 minus log base 3 of the cube root of x squared. Log base 3 of 9 is 2. And I'm going to write the cube root of x squared as log base 3 of x to the 3 over 2. And now our power law says I can bring this exponent down as a coefficient. and this would be my answer over here. Okay, log base 3 of 9. So this is a number. We can evaluate this number to 2, and this is just a simplified logarithmic expression over here. Okay, so in this case, we are multiplying 2 in the numerator, and we're dividing by the denominator. So we're going to use our product and quotient rule for this question. So the same step here, guys. So since we're multiplying these two, we are adding. We can separate those ones using addition for our product law. Since we're dividing by square root of z, I can subtract this one as well. Now, all as well, I'm taking my square root and making it a 1/2 exponent. So this simplifies to. Sorry, now we're going to use our power law. So our power law means these guys can come down in front as coefficients, the exponent. So it becomes 5 log base 7 of x plus log 7 of y minus 1/2 log base 7 of z. Okay, so this is how these guys is written as 3 individual logarithms of x, y, and z for this case over here. Okay, so guys, I always like showing example 6, and it's not quite the same way that the textbook shows this example. But like the reason why we do questions like this is like, relatively speaking, guys, calculators are a new invention. And when I'm saying, guys, like if you look over the last 400 years, like that, well, they've been doing logarithms for years, but calculators and computers are really, I say, an invention of kind of since World War II, like that. So kind of 1940s, like that. And you guys, computers that did logarithms in the 1940s, like that, were massive. Okay, so in the last 80 years, like that, we've had calculators to be able to do this stuff, but before that, they really didn't. Okay, so I say, maybe not even your grandparents, but maybe more like your great grandparents, like that, would have had to solve logarithms like that, but they didn't have calculators to be able to do it. So here's how they did it. They had these things called logarithm tables. Okay, so logarithm tables is like they give you decimal values for different logarithms. So for example, you could have log base 3 of 2, okay, is equal to 0.63, and log base 3 of 5 is equal to 1.46. So you'd open up a book full of logarithms and be able to find these values over here. Okay, now obviously you couldn't keep doing this forever like that. I mean, it's impossible to do it. So if log base 3 of 40 was not available in that book, how would they do it? Well, the way they do it is, first of all, you can break up 40 into 8 times 5, and I can make 8 equal to 2 cubed times 5. Okay, so for our product law of logarithms, I can separate these guys using addition, and that's going to be log base 3 of 2 cubed plus log base 3 of 5. Okay, so you can separate these like this. And now with our power law, I can take this 3 and bring it down as a coefficient. So it's going to be 3 log base 3 of 2 plus log base 3 of 5. Okay, so if we had to solve this over here, and again, we didn't have a calculator, now it's going to be like old school, like multiplication. So we know that log base 3 of 2 is equal to 0.63. So this would equal to like 3 times 0.63 plus 1.46. Let's do this part first. 0.63 times 3. 3 times 3 is 9. 3 times 6 is 18. Carry the 1. 3 times 0 is 0 plus 1 is we got 1.89, which is 0.63 times 3. So now we have 1.89 plus 1.46 would have been 9 plus 6 is 15. 8 plus 1 is 9 plus 4 is 13. Carry the 1. 1 plus 1 plus 1 is 3.35. So this is definitely going to be a rounded value because, this was a rounded value and this was a rounded value. So therefore, this might not be perfect. But on my calculator, so if I just go log base 3 of 40. So I can go math log base 3 of 40, and it gives me so it looks like we did lose a bit of accuracy. And again, since this was a rounded value and this is a rounded value, like we got 3.35, but this guy would have rounded to 3.36. So had we had more decimal places for this guy and this guy, we would have gotten a closer answer for this. Okay, but this is again this is how logarithms were evaluated, kind of like back in the day before calculators were readily available. Okay, so similar one, if we have a log base 3 of 25 over 2. So similar like that. So same thing that we're doing before. This might not have been in your logarithm table over here. So how would you figure this one out? We're going to separate this guy using subtraction because this is a quotient here. So this is going to be log 3 of 25 minus log 3 of 2. 25 is 5 squared. The 2 is going to come down. Okay, so now it's going to be the same thing that we did in the last one. So 2 log 5, and log 5 is 1.46. So 2 times 1.46 minus 0.63. 6 times 2 is 12, carry the 1. 2 times 4 is 8, plus 1 is 9. 2.92. And guys, you're never going to be tested on a question like this, but I think it's kind of it's cool to kind of see how the stuff was done in before. And again, guys, I know we take for granted technology like that. That means we do not need to do all of this like long math anymore. Okay, but we do this, we get an answer of like 2.29. And again, on my calculator, let's see how close we got. Log base 3 of 25 over 2 is so again, guys, it looks like this one would have rounded to 2.30. So like we're off by like 1/100th. But again, it was just like since these guys were rounded values, we lost a bit of accuracy over there. Okay, but again, like that, it's going to give you a very good way of being able to kind of calculate logarithms. So again, in the logarithm tables that they would have had much more decimal places than just 2 decimal places like that. But that's how you kind of did this type of work here. Okay, so example 7 right now, we're just kind of having some kind of longer logarithm questions like that, which we want to evaluate. So again, guys, what's evaluate mean? It means give a numerical answer. Okay, so guys, obviously, I could use this one on my calculator, but I'm going to show you how to do it kind of longhand over here. This is 9 times the square root of 27. So using our product law, we can be able to add these guys. And I'm going to make this guy like a 27 to the 1/2 at the same time I'm doing this. We know that this is log base 3 of 9 plus 1/2 log base 3 of 27. So the 1/2 comes down as our power law for logarithms. Log base 3 of 9 is 2. Log base 3 of 27 is 3. So this answer would be 7 over 2, okay, or 3.5. All right, so over here, we have log 1,000 minus log base 5 of 4 minus log base 5 of 2, okay? So what we're going to do over here is this going to be the same thing as okay, we're going to go 1,000 divided by 4 divided by 2. That's what I'm going to do over here. I'm going to make this 2 with 2 over 1. And so now it's like I'm having like one fraction divided by one fraction over here. So off the side, 1,000 over 4 divided by 2 over 1 is the same thing as 1,000 over 4 times 1 over 2, which is 1,000 over 4 times 2. Okay, now, so it's we're going to see this sometimes over here, and it's just I think some students get confused, like, how did this become, well, if this is a minus, why is this a times in the bottom, okay? And the reason is because we're going 1,000 divided by 4, but then we're also going 1,000 divided by 2, so that's why it's like the 2, but it's 4 times 2 in the bottom, but really it's like we're dividing by 4 and we're dividing by 2, and so like this. So this is the same thing as log base 5 of 1,000 over 4 times 2. 4 times 2 is 8. 1,000 divided by 8 is 125. Log base 5 of 125 equals 3. Okay, so the answer to all this is going to be just 3. Okay, example 8. Express as a single logarithm in simplest form. List restrictions on the variable. Okay, so for this part over here, if we have any exponential function, this part is always going to be greater than 0. Okay, now this part is y is going to be any real number for this guy, but our domain for a logarithmic function is going to be the argument. This part always has to be positive. Okay, so I'm going to do the restrictions first. So for this one, it's telling you that this part, so my argument, 5 minus x has to be greater than 0. That means negative x is greater than negative 5. That means x has to be less than 5. So when you divide both sides by negative 1, we have to flip the greater than sign to a less than sign. So x is less than 5. For this part, we have x minus 8 has to be greater than 0. That means that x has to be greater than 8. Guys, I totally messed up here. All right, quick little typo over here. We're going to go and change that to 8 minus 5 and this to 5 minus 8. And I'm going to redo all this over here. Sorry, guys. So 8 minus x has to be greater than 0. That means negative x has to be greater than negative 8. That means x has to be less than 8. For the other one, we have x minus 5 has to be greater than 0. That means x has to be greater than 5. So in other words, both of these conditions have to be met in order for this combined logarithm to work. So in other words, if we have less than 8 but bigger than 5, that means x has to be in between 5 and 8, like this. So this is going to be the restriction that we have for this question over here. Okay. Now for the single logarithm in simplest form means we're just going to multiply the two arguments. So log base 4 of 8 minus x times x minus 5. So we're allowed to multiply those guys, and I'm just going to expand this out. So this will be my answer in simplest form over here, and this is the restriction for this question here. Okay, so give me a sec here, guys. I'm just gonna do the same thing for this one here. So for this question, we have x minus 3 has to be greater than 0, and that means x has to be greater than 3. So this is restriction for this logarithm. Restriction for this logarithm over here is x squared minus 9 has to be greater than 0. Okay. Now, quick little review, guys. The way that we solve these quadratic inequalities is I'm going to factor this guy as a difference of squares like this. Now, the way we did this one so we did questions like this in Math 20. And the way we did it, we called a number line analysis. So if I draw a number line, I'm going to draw my two zeros over here as negative 3 and positive 3. Now, these are going to be open circles because, again, we're not including these values over here because it has to be greater than 0, like this. What we do is we have to test numbers in each one of these regions. So the region is, if I take a number less than negative 3, say negative 4, well, negative 4 plus 3 is a negative number. Negative 4 minus 3 is a negative. So a negative times a negative would be a positive in this region here. Okay. Negative 3 to 3, say 0, will be a good number in this region here. 0 plus 3 is positive. 0 minus 3 is negative. Positive times a negative is negative. A number bigger than 3, say 5, would be positive, which is positive. Now we want the ones which are greater than 0, so the positive regions. That means we want this guy over here and this guy over here. So the condition for the second one would be negative infinity to negative 3 unioned with 3 to infinity. Okay. Now the thing is, guys, the conditions have to satisfy both of our original logarithms. So if I look at this guy, x is greater than 3, that's going to satisfy this condition over here, but x is less than negative 3 won't. Okay, so the condition for this logarithm, or the restrictions in the variable, is going to be x has to be greater than 3. So this is the restriction for this guy over here. Okay, I'm just going to erase some of this and give myself some extra room. So again, so the other part of the instructions say write as a single logarithm in simplest form. So if I'm subtracting these two, that means I can combine them using division. So this is going to be log of x minus 3 over x squared minus 9, which is log of x minus 3 over x plus 3 x minus 3. And these guys cancel out. We have a 1 in the top. All right, so here is our final answer, and here is the restriction for this answer over here. All right, guys, last example for this section. The pH scale, so this is kind of a chemistry application over here, so I'm sure you guys have talked about pH before in your chem classes. If you haven't, it's okay, we're just going to kind of, we're using this formula. So pH is based off a logarithmic scale. Okay, so it's the pH formula, guys. You may have talked about pH actually before, and it's kind of confusing because you would not have learned about logs. I think you guys learned this in Chem 20, but now you've learned about logs like that, so this is how this stuff works. So pH equals negative log times H positive, where H positive is the hydrogen ion concentration in moles per liter. Okay, so the question is saying cola drink has a pH of 2.5 and milk has a pH of 6.6. How many times as acidic as milk is a cola? So how many times greater is so how much more hydrogen ion is in cola compared to milk? Okay, so what we're going to do here is I'm going to say that the pH, and we're going to do let's do the milk first. So pH equals negative log of H plus, and I'm going to put like an M there, and this is standing for the milk over here. Okay, so in this case, the milk is 6.6. So 6.6 equals negative log H positive for milk. This is the hydrogen ion concentration of milk. I'm just going to divide both sides by -1, so that cancels out there. Now, for logarithms, guys, this is a common logarithm. That means this is going to be an implied base of 10. This means we have 10 to the negative 6.6 equals the H positive of milk. So in other words, it's like, it was really very small. So that means like the ratio of hydrogen ions compared to your solution is going to be 1 for every 10 to the 6.6. So pretty much 1 in every million, something like that, atoms, you're going to have a hydrogen ion in there. Okay, so that's kind of the hydrogen ion concentration. So this is the H plus for milk. Now we're going to do the same thing for cola. So we have the pH is 2.5 equals negative log H plus for cola. So let's put a C there for cola. That means we have negative 2.5 equals log of H plus for cola. That means we have 10 to the negative 2.5 equals this. Okay. Now, what they're saying is how many times more. Okay, so for example, if I said like that, one person has, say 24 grams and another person has 6 grams, one person has 4 times as many. And so you get that by going 24 divided by 6. So if I'm asking how many times as acidic as milk is cola, we want to go and take the H positive for cola and divide that by the H positive for milk. And that will give us the number of times as acidic. So this is going to be 10 to the negative 2.5 over 10 to the negative 6.6. I'm dividing 2 powers, so that means I can subtract the exponents. So to be careful here, because we're subtracting a negative minus a negative, that means we're going to add the opposite here. Negative 2.5 plus 6.6 is 10 to the 4.1. Okay, so 10 to the 4.1, I'm just going to do that on my calculator here. It's going to be quite a big number. So in other words, cola is like 12,589 times more acidic than milk is. Okay, and if you think like that, milk is very basic. It's a very neutral subject over there like that. It's slightly acidic like that, but so pH of 6.6, like neutral is pH of 7, right? So this is like a very neutral solution over here, and cola is going to be a very acidic solution over here, right? But so we're talking about there's 12,000 times more hydrogen ions in cola than there is in milk. Okay, so guys, in this unit, I have a worksheet which is just on like exponential and logarithmic application questions, and this is one type of questions like this. Okay, so we're measuring like pH. There's gonna be questions as well where we kind of measure like sound, like decibels and stuff like that. And there's questions like that. We're also measuring the intensity of earthquakes as well. So those questions, guys, are kind of covered in that other sheet later on, and I'll go over that one in more detail with you guys later on too. All right, guys, hope this made sense, and I will see you in the next video.